And so what I do is I just tell you the place where you can get some of the codes and what popularly people use, and then show you an input file, and Mithul will run it actively and show you how to plot them and so on, those who do not know how to use them. And I'm sure some of you might be already using molecular simulations. For them, maybe the initial part is not very important. So I'm sharing the entire screen, I hope. Can you see the screen now?
Yes.
Yes, we are seeing this.
So I'm showing the codes, which one is called Parkas, which is a parallel cascade. It's a massively parallel code which can be used for cascade simulation, specialized for cascade simulation. And you can see this was developed by a group in Helsinki, Professor Kai Nordland, and he has also extensive lectures in in MD. You can see their lecture notes as well. They are very good. When I was doing MD as a PhD student, I really benefited from those lecture notes. So this is the link, github.com Parka. So you can remember parallel cascade. This is a code which anybody interested in only simulating cascade. This is extremely light for cascade simulations. It doesn't have many other features, like you can look at the input file, for example. So you get all the documentation here, and the input file, which gives you some basic input for different structures. So for example, EAM is a potential which one can use, which is a pair potential, or you have different type of metal, for example, nickel, palladium, any such things, or so for example, Finney Sinclair is a model, and then there's an improved model by Kai, for example. You could really look at his papers for MD simulation in materials, anything related to materials. So these are some of the interesting input file one can send you. It's more or less self-explanatory. All you need, and you have all the instruction to how to make this. Can use GCC to make. You can use G-Fortran, or you can use other Fortran compilers. Can also work in Windows, but parallel feature might not be very good. But I recommend you can go through this, and we use in the institute, we use this as one of the things. Other thing, as already the next speaker also said, LAMS. LAMS is another massively parallel code which can be used for not only for cascade simulations in metals, but it has also wide variety of applicability. And Mithil will show you how to, those who do not know how to install LAMS, will show you a systematic PPT of how the installation can be done in Windows and how can you do for Linux. If you have any queries about it, feel free to contact us. The other thing is visualization one uses is Ovito. Ovito is a what do you call it? It's a visualization tool. It's a free visualization tool. The best part is you can, it's in Python, and those who know Python, or those who can get access to them, they can write little scripts for your own visualization. So this is another tool that one can use. And the pro version, I think, is paid, but you can use the basic, and you can write your own scripts. You can do almost everything with it. So this is a thing you can use. There are other visualization tools as well, like Rasmol, VMD, etc. But currently, this is the light, cheap in the sense it's very light and can also improve a lot. And those who are interested can also write your own visualization. I don't have to tell you that. So this is the starting part. And the second thing is, maybe I'll send you the potential files to everyone. Mithul, can you actually send them right now to the email to Guru so that he can share the potential and the input file to them? And I'll hand over to Mithul. I'll wait here. If Mithul has any question or anybody has query, I'll answer. But otherwise, I'll stay and I'll give the platform to Mithul. Mithul, are you there?
Yes, I'm here.
Yeah. So can you please send the input file and the input file to people so that they can?
Yes, I can send the input file to
Gurudat, yeah. You just please send to him so that other people can also see it, and you can run them live. I'll stay here if you have any queries.
Yeah, I'm sending him.
Okay. So I stop sharing. You do that.
Yeah. So I have sent two input file. One is for relaxation and one is for PK simulation. So student can try that, but that needs a carbon potential. So carbon potential is not available. I am using EDIP. So I'll tell how to implement EDIP potential if someone is interested to do simulation for carbon. So first I will start my presentation with the how to install LAMPS and OVITO. It's very simple. There are only few steps for installation of LAMPS for the Windows, and you can use for Linux also, and it is also easy. So I'll show you how to install. Those who are using Windows platform, I'll show how to install in the Windows. Okay. So I'm sharing my screen. So can everybody see my screen? Hello.
Yes.
Yeah. So you can download the LAMPS for the Windows platform from this link. Okay. And then latest version is from this 5 August 2022. This depending on your 64-bit or 32 bits. So you can download that from this link, and then you can put any drive, C drive or D drive, you to make one folder, and you can install. And then after installation, you will find this folder LAMP 64-bit. Okay, and in there you have different folders. Okay, for the potential, for the examples, and for the PDF, you can find the help documents regarding LAMPS. And then you go to the examples, you can find a different examples. I have shown MEM examples. So and then from there you can go to the command prompt. Okay, and you can run any of the input file from the command prompt. So to run from the Windows, you just open the command prompt, type LMP. I have shown here LMP, and then dash in, and then your input file name. So it will start running in that Windows platform. And once you complete your run, you can whatever data you have, you can dump into the dump file, and then later on you can visualize your data. So you can use the OVITO. Basically, I'm using the OVITO for the visualization and data analysis. So from this website, may have already shown the website link. You can use the free version of OVITO. And this is the screen. Later on, I will show you how to load the input, the data file, and how to analyze the results in the OVITO. So I'll show you how to prepare an input file. Okay. Those who are already using the LAMPS, they may already knowing this, but those who wish to work in with the LAMPS and would like to prepare the input file, for them it is very important. So this is one of the input file I am using for my simulation.
Hello. Sorry
Yeah.
for interrupting. Can we please increase the font size?
Yeah, I'll show you.
Okay.
This increase the size of the screen.
Okay.
No, you cannot do that. Okay. So you can also close the side pane.
Yeah, I'm closing it.
Mitul, you can probably open in the text file itself and show, so you can change the font.
Is it okay? Or should I open in the text file?
That would be easier to write and change. So maybe you can open the text file.
No, the later slide you will find easily,
view,
because this is the
you can increase the view and it will be more comfortable. From the menu, view is there or not?
No, wait. I'll show. This is just for your information. I'll show the later slide. You will find easily. Okay. Like now, is it okay?
Yeah.
Okay.
Yeah.
Yes.
So first of all, you have to prepare, I mean, what kind of units you are going to use. There are different units in the lamps, okay, like LJ, real, metal, SI, CGS. So you can choose depending on your requirement units. So I have shown here metal units. So it is known as style. Okay, on the left side you have the commands. Units is the commands. In the right side you have the style, different styles. Okay, so corresponding to units, you have the style is metal. Okay, so metal means like mass in the grams per mole, distance it will be in the angstrom, and times it will be in picoseconds, energy in electron volt, like that. So if you select the metals, you have to consider the time in picoseconds and distance in angstrom, like that. Okay, then later on boundary. Okay, so boundary is the command and style is I'm taking as a periodic boundary condition. So PPP. So if you are using periodic boundary, you have to write PPP. If you are using non-periodic boundary, you have to write FFF. The next is lattice. Okay. So lattice you can use simple cubic, BCC, FCC, diamond, etc. So I have taken lattice as a diamond, and then next is the scale. Here this is the scale. So scale is your basically lattice parameter. So for diamond, I am taking lattice parameter is 3.567 angstrom. Okay. Then next is region. Okay. So region here, this first is box, that is user defined. So you can give any name like box or cube. It depends on you. Then next is the green color box is block. That is the style. So that style you have to select from the lamps. There are different styles like delete, block, cone, depending on your geometry. Okay, cylinder, ellipsoidal, plane, prism. So there are different style for the region. So I have taken as the block. Okay, and then you have to define the dimension of your block. So let's say your dimension, let's say -10 to +10 in x direction, -10 to +10 angstrom. So or it may be 0 to 10. Okay, it depends on you how you are taking your block. If you are taking origin at the center of the block or center of the cube, so you can take -10 to +10 in x, in y -10 to +10, like that. It is in angstrom. So I have shown here 0 to box L. So this box L is the variable. I will show you. I will show you how to define the variable also. So this may vary. Suppose in one simulation you can take 10 angstrom. Okay. So it will go to 0 to 10. Okay. So this 10 multiplied with this 3.567 will give you in the dimension in the angstrom. Okay. Suppose if you are taking box length as a 10, so 10 multiplied with this scale. In my case, it is 3.567. That is lattice parameter. So it will that will give you in angstrom. So suppose if you are taking 10 as a box length, so 35.67 angstrom will be your box length in x. Similarly, you can select for y or z direction. Okay. So I hope this is clear to all. Any doubt for this, for the box and the boundary condition or the units? So it is very basics. Okay. Next is geometry. Okay. So now you have to actually create a geometry. I mean, how is your crystal? What is your orientation of this crystal or your box? Okay. And so here, create a box. It is already I have given the name box. Already I have given the name the box in the previous slide. So you have to use that box here. And how many boxes you are using? You are using one box. You are using two box, three box. So I'm using only one box in my simulation. So this one represents. You can use any number, 2 or 3, like that, if you have different number of boxes. Okay. And then this lattice diamond. So this specify the orientation of your diamond lattice. So for x it is 100, for in y it is y 010, and in the Z it is 0, 0, 1. So there is no, orientation in any particular direction. So I am using this parameter. Then we are creating the atoms. Okay. So in that box, we are defining a region. We are giving the name region. Okay. And then I have only at present I have only one region in my cell. Okay. I have one box. That box I am going to create atoms. Okay. So what element you are using? Suppose somebody is taking beryllium, so you can use your beryllium. So you have to define in the next line. You have to define the atomic mass of your atoms. Okay. Suppose I am taking the carbon, so I have to define the mass. Again, one here it is for the you are taking only one kind of atoms. Okay, you are not going to take any other kind of atom. So you can specify one, and then atomic mass of your specific to your problem. Suppose for me it is a carbon. I am taking 12.01. Okay, so now in this case I am defining the what kind of atom and the elements I am taking. Okay, and then how I are defining my orientation. Next, I have defined the in my simulation. I am choosing one of the atom. Okay, as a pK. I will tell what is pK. pK is a primary knock-on atom. Okay, so here in this line, second line region RPK sphere 0, 0, 0 and 0.2. So it is the location of the pKa, that is primary knock-on atom. So now I have the entire box with the full of carbon atom. From these carbon atoms, I'm taking center of the cube or center of the box. I'm selecting, that is I'm specifying the location 0, 0, 0. Okay, and I would like to select only one atom as a primary knock-on atom. So I'll later on I will make clear what is primary knock-on atom and why I'm taking this. Okay, so this is the command for that. And then now I am going to divide the entire box into two parts. Okay, one is group 1, that is interatom. I am telling is an interatom, and then at outside I am taking small layer, all the six boundary. Okay, I have in the cube I have six boundary. So all the at the six boundary, I am taking the atom at all the six boundary. I am taking the outer atom. So I have two different regions. I will tell you why I am taking two different regions. Okay. So at present I am taking two different regions. Region 1 I am taking as the interatom. Region 2 I am taking as outer region. So I have two region different interatom, outer atom. Okay. So one will the main interatom will be my simulation cell, and the outer it will be as a thermostat, because whatever extra temperature suppose you have in your during the simulation, it will act as a sink, so it will absorb the extra temperature. Okay, so that is why I have taken the outer atom in my case. Now for any simulation you need to select appropriate potential. Okay, that is force field. LEMS has many potential. I am taking EDIP, that is environmental dependent interatomic potential, which is not there at present in the carbon in the LEMS. So I got this potential from one of the person who is working for the carbon, and then you need to build the potential. Suppose you have the parameter file for your case, then you don't need to rebuild the LEMS, but you don't have the parameter file for the potential. Okay, then you have to build the LEMS for your particular potential. So this CEDIP is the name of the potential I'm using, and in the pair coefficient, this carbon is the atom I'm using for my case. Okay, so it's a basically pair potential for my case, and I am also using the ZBL potential. Okay, so it is user specific potential. It is for my case. Now during the your simulation, first you initialize your box, and then you equilibrate, and then you do the final simulation. So the quantity which you are going to I mean dump into the output file, or you are going to calculate, you are going to simulate. So you have to mention here in the compute. So there are different compute I have used, compute 1, 2, 3, 4, and this compute you can specify depending on your region. As I mentioned, I have defined my cell in, I have defined by atoms in my simulation as inter atom and outer atom. So here I am specifying all. So for all the atoms, I am calculating, coordinates of all the atom at each iteration or each integration. Each time step, I'm calculating the coordinates of all the atoms. I'm calculating the displacement. I'm calculating the kinetic energy of potential energy, temperature. Okay. So this shows the how you have to include, where you have to include the parameters for the computation in your simulation. And then you have to start you have to minimize your model and equilibrate. So here in the, I'm giving at beginning, there are different way to give the velocity to all the atoms. Okay. So here in terms of temperature, so I have taken the random seed here. Okay. And then temperature I'm taking 300 degree Kelvin. Here the temperature is in Kelvin. So this specifies the velocity to the all the atoms. So it will start, you are giving the velocity to atoms, and then later on you are minimizing your simulation box. So there are different technique to minimize your simulation cells. So here I am using the NVT for the minimization. Okay. That means temperature and the volume and the number of particles will remain constant during the minimization. So from 300 to, there are different techniques, as I told, different techniques for the minimization. So from 300 to, relaxation, from the 300 to 300 Kelvin, I am relaxing my simulation box for the time step of 1 femtosecond. Here it is in picosecond, 0.001 picosecond, that is 1 femtosecond. And this will run for 800 steps. Okay. And then during this minimization, relaxation, you can dump your data. Okay. So this line, the last output and run, you can specify what quantity you are going to dump in your dump file. Okay. So there will be a log file also. So you can check in the log file. I'll show you I'll show you the actual simulation. So here you can show the step, size, time, okay, temperature of the atoms. Like in my case, I have shown the inter atom temperature, outer atom temperature, potential energy, kinetic energy. So each time step you can show these parameters. Okay. So after minimization, you need to unfix, because here I have used NVT for the minimization. Okay. So relaxation. So after this, once you relax your model, you have to unfix. Otherwise, it will continue to in the next step, actual calculation, it will continue to fix the NVT. Okay. So you have to unfix first, and then you have to start your next simulation. Before the starting simulation, I have shown you, I have taken the one atom in my simulation as a primary knock-on atom. So what it will do, this atom? So when this atom, I am giving the energy. Okay. Out of all the carbon atom at center, I have taken one carbon atom. I am giving this carbon atom to some energy. Okay. Okay. I am giving, let's say, 2 keV energy to this carbon atom in terms of velocity. Okay. So this carbon atom will knock out other carbon atom successively. So that is called cascade. Okay. Radiation cascade, irradiation cascade simulation. So this is irradiation scenario. Okay. So in irradiation means suppose you have some material, and if radiation falls on that material, okay, what kind of defect will take place in your material? That is called irradiation. Okay, you are bombarding with the radiation to your material, and what kind of defects will generate in your material, how this defect will propagate with the time, okay, how this cascade will take place. That is called irradiation scenario. Okay, so here in my case, I am taking carbon-carbon interaction because my potential is for carbon-carbon. So I have taken the one atom as my primary knock-on atom, okay, and then I am giving that carbon atom as 2 keV energy. Okay, so this I am defining the velocity in x, y, and z direction. So as a randomly, you can give the velocity randomly also. So here I am giving the random. So it will take, initially I will give the Vx, Vy, Vz, and then later on this will propagate. Now, after giving the velocity, it will start the pK run. So during the pK, I am taking this fixed as a NV. Okay, so energy and the number of atom and the volume will remain constant. Okay, so during this NV, I told you I have 2 different atoms. The outer layer in all the 6 boundary, I have taken one layer. So this layer, the temperature I'll fix the temperature. Okay, so temperature will not change in that outer layer, and then you can specify here in fix command, fix 3. You can see here fix 3, fix 1, fix 2, and fix 3. Fix 1, I am giving all the NV. Fix 2, that is outer atom, I am fixing the temperature at 200 Kelvin only. And fix 3, all DT reset. I'm specifying the 2 parameters. Okay, so this is time, 1 e raised to minus 6 and 1 e raised to minus 5. Okay, so this is very important. How to select this time is important. You have to try and you have to do the iteration, and then you can come to know how to select this. Okay, so I'll tell you why it is important in my actual simulation. So, and then you have to dump here whatever simulation I'm doing for the pK. I'm dumping all the data with the time. So I am dumping again the coordinates. I am dumping the kinetic energy of all the atoms and the temperature. Okay, and then this simulation will run up to as per your requirement, as per your desired time. Okay, let's say for 1 picosecond, 2 picosecond, 30 picosecond, like that. Okay, so once you prepare an input file, you have the potential, and then you can start the simulation. So I'll show you how to do the simulation in the lens. Okay. So before that, I hope this how to make the input file is clear to everyone. Or is any doubt? So basically, mainly there are 2 things. First, you have to equilibrate and minimize your simulation cell, and then you, in the second step, you do your final simulation. Okay. So any doubt for till now? So now I'll show how to start the simulation. So this is my LEMS. Okay, and I'll show you the input file. This screen is visible to you. Are you okay with this screen? Font size?
It is visible, but it's great. I mean, it's great if you increase a little bit the font size.
Okay.
We can't see properly.
Okay. Let me check how to
Okay. Press Control plus.
Control plus. No, here it is different. Yeah, okay, okay, thank you. Thank you. So now is it okay?
No. Okay. Okay.
Okay.
One more time. Okay. One more, please. Can you please press one more time?
Okay.
No. Slight more. Okay. Okay.
Okay.
Okay.
Okay. So I have already installed the lens in my computer. Okay. So like I'm using in the cluster, right? Presently I'm using the lens in my cluster. Okay. But if you have installed in the Windows, so Windows, I told you how to just a minute. For the Windows, I'll tell you. Yeah. So those who are using Windows, they have to open the command prompt, okay, and then go to your that directory. So I'm going to show you in the one of the example, okay. Okay. So this in.mem.lmp is the input file. Okay. So just type the LMP, this in and input file name. So it will start the running and then it will stop once your simulation is over. Depending on your problem, it will stop the simulation. So this is from window. Okay. And now I'll show from the Linux. So this is my input file. Okay. And to submit the command, so from the Linux, I can submit my, input file to the, there is a command to submit the job. Okay, I have the job file. So those who are using the, this is for basically parallel simulation. Okay. If your, number of atoms are large, you can use the lamps for the parallel simulation. Okay. So for that, you have to prepare a job file. So this is my job file. Okay. And this is the command. I'm using MPI of the lamps. Okay. And I'm using 400 processor. So Q sub and job. So this will start my simulation. You can check the status whether it has started your simulation or not. So you can see here this 2.02 kV. It has started the simulation. So you can check. and this will also update your log file. So there is a log file when you start the input start the simulation, it prepares a simultaneous log file. So here log file is there, and the size of this log file is 0 because it has not started the preparing the log file. So once the simulation will start, okay, and then it will update the log file at a certain time period, and then the simulation is over, you will get the log file. You have the different data in your output.
Yeah, but aren't these command specific to the cluster you're using?
Yeah, this is specific to cluster. Okay.
Yeah, they will not work on the Linux operating system.
Yeah, they will not. They will not work in this Linux operating system. So I'll not go into that details. So now I'll show them how to, once you have the output files. Okay. Suppose you have dumped all the output files as per your calculation. So how to analyze this output file now? Okay. So in my case, for the defect analysis, I'll show how to analyze the defects, basically vacancy and the interstitial Frankel file, that is known as Frankel file. So how these defects will propagate with the time, okay, when the simulation will continue. So I'll show you that. So for that, I have the dump file is TFP 1.1. This is my defect file. Okay. So I'll show you how to analyze the data in Ovito. So you have this Ovito, you load the file. For particular run, I have this TFP 1.1 file. Okay. So you can see here all the atoms of your models in the Ovito. Okay. Now I'll show you how to analyze the defects. So there are different options in the Ovito. Okay. Depends on your application. So for the defects, I'm using Wigner set defect analysis. Okay. So select that. Okay. So now I'll select all. I'll not select all the atoms. I will select those atoms. Okay, which has removed from or which is displaced from their position. These are the original position of the atom. Okay, so I'll because if I take all the atoms, we will not be able to see the defects part. So I'll hide these atoms and I'll select only the atoms which is removed from their original position. So select the expression. Occupancy equal to 1. Okay. So initially I have select all the atoms. So this occupancy equal to 1 means those atoms which are there at original position. Okay. So I'm highlighting this atom only. Now next step, I will delete all these atoms. So delete selected atoms. So now all those atoms which were initially there at original position, I have deleted all that atom. Okay. So now it will only highlight. Now it will highlight only the atoms which have moved from their original position. So here I can, with the time, you can see the defects. So here at time equal to 0, all the atoms are at their original position. Okay. So now I'm increasing the time. Just a minute. Before that, I am giving the color coding so you can identify. Can you see the atoms in the screen? Can you see my screen? Hello?
Yes.
Yeah.
Yes, we can see.
Yeah. So are you getting or not what I'm doing it presently? I am showing you how to analyze for the defect. Okay, so there are different technique to analyze for the defects. Okay, so in Ovito I am using the Wigner-Seck defect analysis, and defects means I have told you in my simulation at the center I have taken one atom at the center, and that atom is, for me it is a primary knock-on atom. How this primary knock-on atom, what is primary atom basically? So when suppose you have any incident particle, suppose in my case I have the neutron is my incident particle. So when it hits my simulation cell, it will remove one atom from its position. So that atom is, for me, it is a primary knock-on atom. Okay. So now once you have one atom, this atom will remove other atoms when it moves from its position. When it moves with the time, it will knock on other atoms. Okay, so you have the vacancy and interstitial. So that vacancy and interstitial is known as Frankel pair. So suppose you have one vacancy and one interstitial, that is known as one Frankel pair. Okay, so this how these Frankel pairs is evolving with the times. I am showing that, and these are known as defect. So at present only one Frankel pair is there. Okay. As time goes, you can see this red atom, it is moving with the time. Okay, because it has the energy. See now, you have two interstitial and two vacancy. Suppose let's say two red color is interstitial. You know interstitial and the vacancy. Okay, so from the one now you have two. Again, so with the time, you have large number of interstitial and vacancy. Once it loses its energy, okay, so at present you have 20 interstitial and vacancy. You can see here right side bottom found 20 vacancies and the 20 interstitial. Okay. Now it will start decreasing. So this way you can analyze your results of MDIP simulation into the Ovito with the help of Ovito. So you can see here the defects has stabilized now. So you got initially there were no defects. As time goes, defect starts increasing. They will, I mean, in the crystal, you have the large number of Frankel pair over a period of time. Okay, and then later on, the defects get maximized, and then again, you have the probability also recombination. So they may recombine also. Whatever vacancy and interstitial are there, they may recombine. Okay, and then finally you have the number of defects, stable defects. So they are known as stable defects. So they will not increase because your pK, whatever pK energy you have taken 2 kV, so that energy is now stabilized. So there is no defects. So there are different data, different parameters we in the simulation we do. One of them was, in my case, was the defect analysis. Okay. Again, displacement is also there. How defects and differentiation are different. Okay. So displacement means the atoms who have moved from their original position. Okay, they are known as the displacement. So there may be different displacement also. So different, you can analyze for the displacement also, defects also, for the cascade also, like that. So this was the one of the example I have shown you in the OITO. Any doubt for the OITO for the defect analysis? Are you people are using OITO for any visualization and analysis? Any student is using OITO? Hello.
No, anyone, no one is using OVITO.
Okay. Then which kind of I mean tool you are using for the visualization? Or you, I mean, you are not doing the simulation for using lamps or?
Maybe they are not using lamps.
Okay.
And maybe not radiation simulation. So what probably you are showing
so
is
this problem I have shown is specific for the irradiation scenario.
Yeah.
Okay. There may be different scenario, but I am doing the irradiation scenario. That's why I have shown you the irradiation scenario. And then my file is only specific for the irradiation. Okay. So I have sent the files, or you can make your own files also, input files, and you can run in the lamps. If you have any doubt, you can let us know. We can help you. Whatever we know up to that level, we can help you.
Mitul, maybe you can also show what can they do with lamps, like something, OVITO with something like, you showed Wigner seeds analysis. You can also show different expressions, and there is.
So far, ma'am, I have used only for this occupancy one money only. That is for defects.
Okay.
So I have not used any other extensively. I have not used the lamps. This OVITO.
So expression is basically, so the occupancy is basically telling you whether the atom is occupied there or not. So ideally you want to have every atom to be occupied once, right? So if it's perfect lattice, you have single occupancy. But if you have occupancy less than 1 means you have a vacancy. And occupancy more than 1 means you have an interstitial.
Yes.
So that was that thing. And you can.
That is why we are giving occupancy equal to 1. So
right. So you're deleting those layers.
Yeah, I'll delete those atoms.
And it can also use for seeing lattice structures and other things. Probably that is what the next speaker probably show, that how in grain boundaries and nanostructures can be shown. Maybe we can see that session in more detail where they show. Yeah. Okay. And you could also send those files, the PPTs, so that they can use it if they want.
I will send them a simple input file with the potential, so that they will try. They can try later on, and if they have any doubt, they can, I mean, contact us. So my from my side, it is over. Any doubt, you can.
Anyone of you have any questions?
Could you actually try this online in the Windows versions if you have? Could you try those simulations, or was it successful from your side?
Actually, ma'am, for Windows.
No, I mean the people who are doing this there. Could anyone try that input file, or?
Okay. Hello, ma'am.
Yeah.
You did not send potential file.
You did not send the potential file?
Yeah, because I'll send the potential file, because my file is for the carbon. So
okay, so I will send you another potential file which you can try.
Okay.
So I think I had attached this file here somewhere. I just sent to Guru's email, potential and input file.
Okay, ma'am. We'll share with these students.
So they can share. This is an input which we developed here. I mean, we included with our own requirement. So probably it's not very universal.
We have a question here. So
Yeah, sure.
Yes. So, ma'am, in LAMPS file, there is a command for kinetic energy per atom and potential energy per atom.
Right.
Calculate, right?
Yes.
So,
Yes.
what's the difference between this kinetic energy and potential energy and the kinetic energy and potential energy you are printing using thermo command? So, this
So
was
this
the
is
same.
the one is the average kinetic energy. The other one is the individual kinetic energy. Total the KE you get the total energy. This is individual atoms potential energy. If you want to let us say simulate strain in the lattice or some such individual local properties, or you want to see whether there is a defect from the potential energy difference, then you need to print the kinetic energy per atom.
Okay.
That's the
So,
potential. That's a more microscopic atomistic picture. The other one is the overall energy of the system.
okay, thermo one is the oral energy, right?
Yeah, thermo calculated thermodynamic properties of the system. Of system is to define, like you say 100 atoms as a group or a division or what do you call a region or something you define. So you can have a group of atoms or a class of atoms, let's say, which are having a different property. Like for example, you say hydrogen atoms only, or if you want to do tungsten, or you have an alloy, let's say steel. So steel has different components, right? So if you want to have a particular class or a group, then you can also do the thermo of that, average over that. But individual atom per kinetic energy per atom is individual. There is a good documentation of the lamps in the website itself. So you can see the difference, and I'll just send you some. You can vary the scale and other properties, okay? Because these are just things which you can try them out. So
Thank you.
you can reduce the number of atoms. You don't need to do that many atoms. You can, as Mithun showed, you can reduce the size, and then you can run them also.
Okay. Thank you.
Yeah.
So any other questions? People online?
You can try this, and you could also look at another interesting thing would be to look at random number generation and see how good the random numbers you create with different tools. So this would be an interesting test for confirming our own results. How good are they? How reliable are they? So this is something I think everyone who does atomistic simulation should try. So yeah, that's just a suggestion.
Okay. So, okay. We have one more question.
Yeah.
She is coming.
Yeah, sure. Good.
Good morning, ma'am.
Good morning.
Ma'am, here we are doing MD. In lamps, there is only classical MD. When we talk about plasma or say be it warm dense plasma, is it enough to use classical MD to calculate various properties, or do we need some DFT calculations in addition to classical MD?
So molecular dynamics simulation in the conventional sense use only the classical MD. Classical MD in the sense you get all the properties from the quantum picture using DFT, and then you look at the evolution in the classical frame. So you use the approximation of Born-Oppenheimer approximation, where you imagine that the time scale in which the ions evolve, the electrons are already finished their motion and they are at rest, or they are at, giving a background to the ion motion. So you're looking at a slightly larger time scale. But in the DFT, on the other hand, you're looking at the electronic picture. So if you want to do quantum picture, yes, you need to do the quantum picture, quantum calculations. There are also quantum MD techniques you can use for high energy physics, for example.
Correct.
But in this thing, you will ask me then why is it that the condense matter is all quantum mechanics? Yes, it is quantum mechanics. And what you do is take out the essential feature from MD. So you create the potential from the DFT, or maybe even more ab initio calculations, and then you parameterize in such a way that you can create all the macroscopic properties correct. So it's not a single scale problem. Your potential generation involves a lot of DFT and ab initio calculations, and then you come to the quantum, the classical picture. So, taking the potential has the properties of quantum in the ground state. Now, if you want to do something like excited state, for example, one thing that I didn't show is, could you mute at your end for the time being? You can start again.
Yes.
Yeah, it's echoing quite a lot. So one thing which I didn't show in the talk was there was a the way the ion. So for example, when I just share the screen once again. So if you look at the way the ions, can you see the screen now?
Yes, ma'am.
So when let's say we create a pKa and the pKa goes through the lattice, it gives a part of its energy to the electrons in the system. So in a fundamental sense, the electrons are also getting excited and ionized and so many processes happening. And if you look at the electronic laws, so what happens is that ideally the electron could go to an excited state, which you cannot simulate using MD, which you cannot simulate using conventional DFT either, because the DFT also looks at the ground state property. So you should do a real excited state calculation with ab initio. That is the ideal thing to do. But we cannot do that because there you are severely compensated or constrained by the number of atoms can you use. Therefore, what one does is one does those calculations and find out what is the total electronic loss to the electron system. Then you imagine that there is an electron cloud as the ion moves through the lattice or in the plasma. It is the same thing. Basically, at that picture, you can imagine it is like a plasma only. So that as the ion move through the plasma or the lattice, it gives an electronic system an energy which is proportional to your velocity. So it's like a frictional force that you simulate. Then you subtract that energy and do the ion part. So you say that this much energy is going to the electron system, which is not going to affect my defect, but it can defect formation, but it can affect your, for example, in semiconductor, for example, if you do the same thing, then this loss to electrons can actually create tracks. And this is one of the, this is one of the problem why solar cells fail sometime, because you get this ion bombardment in the space can create tracks in the system. So there you have to use the full quantum calculation. So it depends on the problem that you have. And as you correctly said, in the plasma case, or if you if you want to have electron excitation, then you should do a full calculation. If you can stay with the quantum picture, but still in the ground state, you can do the conventional DFT. Here we take those output from the conventional DFT. So when you take a potential, so why do we have different type of potentials? Because why can't you simulate everything with the same potential? Because the potential actually takes care of the quantum mechanical property of the system. And I want to tell you one more thing there, that if you go for a there is a huge noise.
Someone mic is on. Kausal, please.
Somebody's microphone is on. Yeah. So thank you. So what happens that if you want to simulate, let's say, you know that DFT is takes into account a functional of electron density, which is basically taking into account the, so let's say if it is carbon, you have S and P electrons, right? So you have 6 electrons altogether, and this is S and P. So you can kind of completely develop a functional with that. But if you have tungsten or even gold or any other heavy metal, then you have 70 to 100 electrons, and you can only do a function of valence electrons. So to some extent, you can simulate the valence electron properties. But if you really want to look for a truly excited state calculation, like you give a 1 GeV energy, then the electron will go to, let us say, it may ionize or it may be excite to very high inner electron state, then these methods have its limitation and they're not really the best thing to use. Then you really go to the pure quantum picture. Then you do the whole multi-scale. That is why the multi-scale picture become important. You can't do with a single scale problem alone. Yeah. So, yeah, please.
Yeah. Thank you, ma'am.
What do you do? I mean, you are doing for plasma quantum calculations in is
Uh,
it like neutron stars or
No, I'm working on metallic glasses, but in my group, in my lab group, we are also working on in Womden's plasma.
okay, there you have quantum picture. Yes.
Yes, yes.
Quantum
So,
MD is also there, but there you are limited with the number of particles. So you might need to do multi-scale there.
okay, okay. Thank you, ma'am.
Yeah, sure.
Ma'am, I have one question.
Yeah,
I think it's more a question is advice. So in future we are planning to do warm dense matter calculation for refractory materials. For
What
molybdenum.
calculations?
For warm dense plasma state, we are aiming for high Z material, refractory materials. And you have very great experience in this field. So any advice or anything that you should look after?
What kind of problems are you looking at? Basically, what do you want to do with MD there? What is the
In refractory materials, mostly you said that it's in the outer core. You can use molybdenum or high Z materials.
Yeah. So you are asking me, are you asking me like, can you use a DFT to do there, or is it?
Yes.
You can do DFT, but it depends on, see, if you were looking at, there are two ways to look at this problem. If I say more fundamentally, all our material properties are decided by the core electrons, valence electrons, right? All your binding energy, everything. So if you want to look at problems of that kind, then you can do a DFT. But if you really want to look at the core electron properties, systems where the core electron property, like high energy density plasmas, for example, there one has to probably look at more into the ab initio level, I would think, if you want to really truly get. But again, it depends on what you want to look, because it's a problem dependent thing. So sometimes you can get the ab initio calculations parameterized so that you are still able to explain a large number of macroscopic properties with conventional molecular dynamics by changing its, of course, the potential can take it. See, think of MD is like one uses molecular dynamics algorithms for let's say that you might have heard this Millennium Simulation, which is a large galaxy simulation where one was using this to, it was a huge paper in 2010 it came up. So if you look there, what people did was they were using gravitational potential and then using molecular dynamics to evolve multiple systems. So you scale it up, but you ask this question, yes, you can simulate such kind of things as well, but then you need to have a proper parameterization. So unless you can explain me something more, maybe in mail, I'm not able to offhandedly tell you what exactly you should look at. So if you are more interested in the core electron properties or more like high density plasmas, there, if the core electrons become important, let's say, then you need to do a full ab initio. But if you can email me the detail, I can probably help you a bit more.
Thank you, ma'am. Thank you very much.
You can also look at Millennium Simulation, which was one of the landmark. It's basically MD algorithm, although they tell you it's a very different galaxy and all, but it's basically the algorithm is molecular dynamics, potential. You solve particles in potential. That's the story. Yeah.
Okay. Can you repeat the name? What?
Millennium Simulation. You can look at the large, massive parallel simulations in galaxy formation, galaxy interaction.
Okay.
Yeah. Okay. Millennium Simulation. It started in 2000, and I think it took almost a decade or so to finally come to this thing. It was a huge.
Thank you.
Yeah.
Thank you very much.
Ma'am, could you please explain the part of installation of lamps where we deal with the MIM file actually?
Part of installation of MEAM. I think Midul can give you that link. So where did you have the doubt? Midul, are you there?
Yes, I'm here.
Could you show, you have a problem with the installation or the problem with the MEAM concept?
No, after the installation for to run the lamp.
Okay.
Okay. Midul, could you please explain?
Yeah.
Thank you.
So you need to go to that folder, particular in example. Okay, you are there in example folder. Hello,
Sorry, what?
are you there in example folder?
Uh, Sir, could you please
yes,
share the
yeah,
screen?
exactly.
Yeah, okay, I'll share my screen. So basically, suppose you are there in example folder and you are talking about MEM. Okay, so go to that folder. Okay, now you right click. Okay, and then click select any I didn't console here. Like in my case, I have two console here. Okay, command console. So you can directly get that path here. Or if you don't have that option, from the command prompt, you can go to that folder. Okay, MEM folder.
Okay, sir.
Okay. Suppose now you are in MEM folder. Just this is the executable. LMP is the executable. Okay. LMP dash in dash your input file name. Suppose our input file name is okay. My input file name is here in dot okay in dot mem dot lmp. So this will run like this. Okay, it's a very simple input file. So like that, you can go to other folders also. You will get a different example, and you can make your own input file and you can place in any of the folder. So that is the same. I mean, I answered your question or something else.
Yes, yes.
Okay, so you got the how to run.
Yes, sir. So after that, it will run, right?
Yeah. So then, so once you run is completed, okay, you can check the output file also. So I'll show you. So this is the folder. And this log.lamps is the output file. Latest is 12:48 p.m. So it is the output file. You can open that file. Okay. So this is the output file. So that means this has run. Your simulation has run, and there are different. I mean, time step is there, temperature is there. Okay. So it will show you the parameter, whatever you put into the input file. So likewise, you can make your input file and then run. And you can also download the, if potential is not there in the folder, you can download the potential also from the, there are different repositories on the online. Okay. So like I'll show you. Potential for lamps. Okay. So you can go to this website. Okay. Suppose suppose I select the silicon. Okay. So select the silicon. So you'll get the potential from here. Parameters file for the potential. This is terms of. Okay. So this is the potential file. So this potential you can copy and you can make a file from this parameter. You can place in your working directory. Okay. So there are different potential for different elements. You can take from this ctcms.nist.gov website. Okay. Anything else?
No, sir. Thank you.
Okay. Okay.
Yes. Are there any other questions? No, if there are no more questions.
I have shared a link about the Millennium project, so we can look at that later on. I mean, you can share them so that they can see what kind of, I mean, it's not called MD, but still the same method or the technique can be applied. And I'll share a link on the core electron physics once somebody asks this question. So I'll share the link also.
Fine, fine.
We can share them later. And Midul probably might share all the PPT of
Yes,
the
yes,
slides
yes.
of how to install. So you can share
I will
more
share
details.
one simple problem, okay, so that you can realize the potential and then how is it is potential, how your potential is behaving. Okay, I'll share that detail.
All right. So if there are no more questions, let us thank Dr. Maya and Mr. Mithul for those wonderful sessions.
Thank you.
Thank you. It was
Thank
a
you very
pleasure.
much.
Feel free to contact any questions. If we can answer, we will definitely help. And we will also learn. So it's good.
Sure.
Yeah. Okay.
Thanks a lot.
Thank you, everyone. Bye.
Bye bye.